All right, here we go. So the last section in this very long chapter, chapter 3, which is all about derivatives, is 3.7, which is derivatives of inverse functions. Okay. And so let's just run through our list of what we know, AKA things that we should study for Friday's exam. So what we know, we've talked about average and instantaneous rate of change. We've discussed the formal definition of a derivative. Now that formal definition of a derivative, does it correspond to the average rate of change or the instantaneous rate of change? Exactly, that formal definition, we want to really tie into that idea of instantaneous rate of change, right? Now that is the long way to do a problem, because after learning that formal definition, we've really focused on all of the rules, so many rules, okay? Now, for better or for worse, I know that a lot of the quiz questions that we've been looking at mix a lot of the rules together. I hope that that has, even if it was scary at first, has actually started to help you figure out a thought process that works for you in terms of identifying the rules and knowing when to use which one. Okay, because in addition to knowing the rules, what I really want to set us up for is that decision-making process, right? That problem-solving brain, because I think that's something that you can take with you no matter what class you're taking, right? And so we're going to cap off this unit with how do we find the derivatives of inverse functions, okay? So that's not something we've looked at yet, though we've looked at a lot of other rules and thought about when we might want to use them, okay? And so we're going to start right here with this theorem, okay? So this theorem, the inverse function theorem, looks like this. So give you a moment to read that over. And as you're reading that over, I'd love to hear in the chat maybe one thing that you're like, oh, I know what this notation means. Or one thing where you're like, I don't know what this particular notation means. Okay, so for example, someone might say, I know that this symbol means that it's not equal to 0. Okay. Or someone else might say, y is just another name for g of x. Okay. So yeah, let's start putting some ideas in the chat, or annotating on here is absolutely fine as well. What are some notation things that we feel like we understand, or maybe we still have questions on, right? So good, good. Okay, so that -1, Christina, I saw that you underlined that, and that Thea, you circled that, and Yuthan is talking about that, f of the -1. And so that might be something that if we look back in here, we see that f to the -1 of x is the inverse of x. Good. All right, so we've got that prime notation means the derivative. Good. Okay. And I'm gonna ask you to pause for a moment. I noticed that someone underlined this one, and I'm wondering, was that underlined because it's something we understand or because something that we're not clear on? Okay, and so I'm wondering if we could maybe rephrase this. Like, what is this saying? If we were to write it out in words, what is that saying? The derivative of the inverse of f of x. Okay, so the derivative of inverse of f of x. I like that. I like that. Okay. Now, I think I cut someone else off who was maybe notating. Ethan, I think it was you who's notating down at the bottom here. What were you about to notate? Or anyone else who was annotating here? What else might look familiar or accessible to us? Oh, looks like chain rule, but we divide instead of multiply. That's an interesting observation. I like that. Anybody else notice that when they were looking at this part down here, that like we're only taking the derivative of the outside part? That's kind of like the chain rule. Okay. All right. I love that we've started with this strength-based lens where we're looking at the things that we know. And I'm wondering what kinds of questions are coming up for us here. Okay. So before we move to the question, I noticed that someone said that that fraction here looks like a reciprocal. So I just wrote that down. Okay. I think that's a really good observation. And let's see, why can't it be 0? So let's go back to this idea. Why might we think that something cannot equal 0? Because we've kind of seen that before. If we think back to I think we called it rational functions. And maybe we had like y equals 1 over x. And a lot of times, maybe we didn't notice this so much, but we would say x cannot equal 0 in that case. Okay. So we so often focus on this part that sometimes we don't write that part out. But I think it's something that we kind of knew, that it's a problem when we have 0 in the denominator, right? And so I wonder, let's double check what they're saying is not equal to 0. It looks like they're saying the derivative of something cannot equal 0. And if we look at the equation, they're saying this cannot equal 0. And I think they're saying that because it's the same reason as you would tell me in the rational function y equals 1 over x, that x can't equal 0. Okay, which is exactly like we said in the chat, can't have 0 in that denominator because dividing by 0 causes a whole bunch of problems for us. Okay. So I think hopefully that clarifies why we have that not equal to 0. Okay. Let's take maybe 1 or 2 more things that we're like, I'm not really sure what this means. That word invertible. Okay. Okay, so invertible, and when is it not invertible? Okay. I think this might be something we can kind of come back to after we take a look at that Desmos activity, because when we go through the activity, I think it might come out why certain things maybe are restricted versus why they might not be restricted. And that might help us answer that question. Okay. Anyone sitting here being like, what does this even tell us? Like, this is so overwhelming, because I know for me, the first time I saw this particular formula, it just has a lot of like stuff going on with it. So if you're feeling that way, know that you're probably not alone, okay? I wonder if, just like we were able to turn this into words, like we said, the derivative of the inverse of f of x, okay? I'm wondering, before we go to the Desmos activity, can we turn this into words? Or can we turn this into words? Okay. So looks like we've gotten a potential guess for this in words. Okay, now how could I write g prime of x? Like, how might I be explaining that to someone who might not know what a prime is? What's another word we could use for that? Okay, so maybe we read the left-hand side as g prime of x, but maybe if we were explaining it, we would say that the derivative of g of x is equal to, okay, so we've taken just that left-hand side. The derivative of g of x is equal to, okay, 1 over f prime of g of x. Okay, how might we be able to use some other language instead of just like writing the formula as it is in words? Like, what are some concepts or other ways that we could describe 1 over something? Okay, something to the power of -1. Ah, okay. But really, when we have 1 over something, we're thinking about that as a reciprocal, right? So derivative of g of x is equal to the reciprocal of what? What is it the reciprocal of? hang on real quick. This is that a minus sign in front of the 1? Or is that an accidental marking that got left there? Ah, that's an accidental marking. Okay. So let me just kind of move that a little bit. All right, so there's no negative in front of there, but okay. So the last part of the theorem explained the same way, that 1 over, oh, I see. This part right here. It does look really similar, yeah. It looks pretty similar to this part or to this part. Okay. All right. Any brave soul want to try and finish this statement right now? And it's okay if we don't feel like we've got a good statement for this. That's okay. We can, I think it'll be more clear after we do the Desmos activity. Okay, I like this. So derivative of g of x is equal to the reciprocal of the derivative of f of x with an input of g of x. Okay. So I have to say, I am hugely impressed with sort of the collaborative nature, all the things that you folks are sharing here, because in the past I've asked folks to, say what they know, what they don't know. And mostly it's been, I don't know what any of this means. Like most folks are just looking at this being totally stuck. Okay. So that is so awesome. All right. That no matter what it is, finding something that you can say, I know what this means. That is such a great place to start. Okay. So on that note, let's do this. I'm going to stop sharing my screen for a moment. Okay. And if you sign into your Desmos classroom, okay, let me just type these directions in here as well. You're going to sign into your student Desmos account. Okay. And underneath that account in our class, there should be a new activity that is called Introduction to Derivatives of Inverse. Okay. And so I noticed that several of you have already started that activity, which is awesome. And my question for you before we, excellent, so many folks. Okay, I'll give everyone else a little bit more time to get into their Desmos account. So my question for you is this. I know that sometimes it's beneficial to be in breakout rooms, but that seems like maybe it's been sort of hit or miss in the last few rounds, or sometimes we get to like a specific point and we feel stuck. And because you're in breakout rooms, it's a little harder to ask for help. So I'm wondering, how would we like to approach this Desmos activity? We can kind of go through it together. Or we can all just kind of work on this individually, and then as questions come up, you can sort of put that in the chat. So I don't have to send you anywhere, but we can sort of collaboratively figure out what questions we have. Or I could also just share the screen and we could kind of talk through it together. Anyone have any preferences? do it together? Okay. And you can always come back. So if you're not signed in, that is absolutely fine. You can always come back and do this later on. Okay. So with that, okay, cool. Let's see. Okay, so let me go ahead and share my screen. Da, da, da. All right. Oh, sorry, that's annoying. Hold on. Okay. All right, so in your Desmos activity, this is the very first slide, okay? So I'll give you folks a moment to look over this. If you have your version opened up, you'll notice that there's sort of a red point and a blue point on the red point on the red curve, blue point on the blue curve. And if you click on this, you can sort of drag them. And when you drag the red one and the blue one, they sort of, or if you drag the red one, the blue one also moves, okay? And so play around with that for a little bit. You can play around with that on the linear graph, or you could play around with that on this other graph over here on the right. But what I'd like us to consider is these two questions. So for both graphs, what do you notice about the relationship between the coordinates of the red point and the coordinates of the blue point? All right, so that's one question. So let's take a minute, move that point around, use that slider, see what patterns you notice, and then let's write down something together. And so once you think you've got a pattern, type that into the chat or unmute yourselves and we'll collaborate and come up with an answer. Okay, so we've got one idea, the X and the Y on the points flip. Okay, can you be a little bit more specific about what you mean by flip? Like, am I taking reciprocals? Because reciprocals are flipped. Ah, okay. So one X is the Y on the other point. Okay, so let's see. I think looking at all of the contributions we have so far, maybe it's fair to say that the X value of the red line, or it could be one line. So the red line is the Y value of the corresponding point on the blue line. So the X value of a point on the red line is the Y value of the corresponding point on the blue line, okay? So something like this, I think, is us being really specific in our language, that we're not just saying flip or switch, but we're really showing like a very clear understanding of what's changing versus what might be staying the same, okay? Okay. You could, if you wanted, you could say similarly, the Y value of a point on the red line is the X value of the corresponding point on the blue line. Okay, so something like that could be a response. So when you're thinking about things where I ask you to sort of explain your thinking on an exam, something like this where we're really trying to be specific in our language, I think is really valuable skill to practice, okay? Now let's take a look at the second question. So numerically, so looking at the numbers we have, how can we determine that two functions are inverses of each other? All right, so think about that question for a moment. If we know that the red and the blue lines are inverses of each other, how could we tell just by looking at the numbers that they're inverses? Okay. So this might be something that you remember from once upon a time in your mathematical journey, that two functions are inverses of each other when the pattern that we noticed is true. Okay, meaning that, see, I think I can just copy and paste this. When, no, that's not what I wanted. When the x value of the x values of points on the red graph are the y values of the points on the blue graph. Sometimes we refer to this as switching the x and y values. Okay, now that might be a phrase that sort of jogs a little bit more of your memory, that when we're thinking about inverses, we're taking our x and y's and we're just swapping places, right? So that is a sort of catchier way to say what we said in part A. All right. So how are we doing so far? Thumbs up if we're doing great. I think there should be a place for that in your, yeah, we see a couple thumbs up, or you can just type into the chat that it's great. Excellent, excellent. Okay, all right. So keep this in mind. We're going to come back to this idea. All right. All right, so next slide, inverses. All right, this is where I need your contributions right off the bat, which is, what are some things that you remember about inverse functions? So I'll give you a moment to kind of think about that. So if you've never heard of them, we could click here. If you know a property of inverses, we could click here. If you had an example of inverses, we could click that middle one. And again, once you've had time to think about that, throw your contribution into the chat. Could be any of these. Okay, so what are the examples then? Oh, I like this, I like this. Okay, so one example would be, and if you want to type in like a math function, if you go to this little square root button here, it says type math, and then you can say like f of x equals sine x. That's one function, right? And go back to that type math. G of x equals sine to the -1 of x, or a pair of inverse functions. I agree with that. Anyone else have a specific example of inverse function? Yep, we could do that with any of the trig functions. So we could replace sine with cosine. That would still work. We could replace this with tangent and inverse tangent. That would still work. Okay. We could say that. Let's go back to that math type, y equals x squared. And math type, y equals, anybody remember how we get that square root symbol to pop up in Desmos? Yeah, square root of x. Those would be a pair of inverse functions. Now, actually, I think this is a great time to come back to Ethan's earlier question about like, when might something not be invertible? So this y equals x squared, like give me some numbers that I could put in for x in the y equals x squared. What could I put in for x? 2, I could put in 2, yeah. What else could I put in? 4, 5, okay. Could I put in pi? Yeah, okay, I could put in -3, 2. All right, now what about with its inverse function though? Y equals square root of x. Okay, so exactly, right? We can, if we're only working with real numbers, everything under that square root must be 0 or greater, okay? So that's why sometimes we say that a function must be invertible, okay? Otherwise, we're gonna have to do some things like restrict the domain. Because if there's some numbers that we can't flip, like, because when we do the inverse, we can't actually get a number out, then we have to think about restricting domains or restricting the kinds of numbers we can put in. Okay. So if I click share with the class, that should be a response that other folks can see. But if we go back to this graph for a moment, this red curve right here is the right half of a parabola. Like when I wrote this graph, this curve I wrote as x squared, but only for 0 and up. That's why we only see half of it, because I wanted us to be able to see the part of the graph that had the inverse. So not the whole graph has the inverse, only part of it does. And that's why we see this blue curve right here. Okay. All right. So let's take a look at scenario 1 here. All right. So pick a point on the blue curve, find the slope of the line tangent to the blue curve at your selected point, and then find the corresponding point on the red curve and find the slope of the tangent to the red curve at that selected point. Okay, so this is where I'd like you to kind of play around on yours. Pick a number, pick your favorite number. I bet among the class we have a lot of different favorite numbers, so it would be really nice if not everyone picked 1, 2 and 2, 1. Okay, so move that slider around. You don't have to pick a decimal number. You can pick a whole number is fine, but let's try it in the class to maybe get like at least 3 different numbers and thinking about what the slopes are at those numbers. Okay, so I'll give you a moment to do that. Pick a point, find out what the slope is, and then let's, in the chat, let's be specific. So you said 0.5 or whatever on the blue graph, here's the slope. All right, so tell me what your point is, tell me what the slope is for the red one and for the blue one. Okay, we've got one value, so at x equals, no, at 4.6 comma 2.3, the slope is 1/2. Okay, and her corresponding point at 2.3 comma 4.6, the slope is 2. All right, very nice. Let's get maybe 2 or 3 other examples. So just like that, tell me the point and the slope for the blue one, and then tell me the point and the slope for the red one. Okay, so right now we're just drag your points along, pick a point. All right, so just like Natalia had in the chat, you're just typing in a point and the slope there, and then a point and a slope, okay? Okay, so let's see, let's at 2.5 comma 5, the slope is and okay, and you have the corresponding point at 5 comma 2.5, the slope is 2. All right, thank you, David. All right, let's see, Chance says at 3 comma 6, slope is 1/2. Okay, and a corresponding point. Do you have a corresponding point, Chance? Am I missing it in the chat? Okay, so at 6 comma 3, the slope is 2. Great, let's grab one last value here. Let's see, Christina, you've got, okay, at 8 comma 4, the slope is 1/2. Good, and then your corresponding point at 4 comma 8, the slope is 2. All right. I know I didn't capture everyone's points here, but I think this looks great. All right. So first of all, in case there might be someone sitting in here being like, I don't know how everyone found the slope. Can someone just remind us how we find slope from a picture? Yeah, exactly, right? We can count rise over run. And sometimes that feels so long ago that we forget it's a skill, but we can always just pick some points and count rise over run, okay? And so what do we notice about our points here? Like before we move on to the next slide, what are some things we notice about the points and their slopes? Okay, so I want us to be really specific in our language here, okay? So when we see the slopes are opposite of each other, like I see a 1/2 and I see a 2, I agree that in some sense, there's some sort of opposite, but yes, exactly. I think that word reciprocal might be a better phrase here. That the slope, yes, that slope of one function, the slope on the other function is the reciprocal of that slope, okay? And what do we mean by the slopes are corresponding? I wonder if we could unpack that a little bit more. Ah, okay, the slopes are reciprocals. Okay, cool. So I think if we look at all these numbers from the blue curve, we got 1/2 all the way. And then when we look at the slopes of the red curve, everything was 2, right? So for every point, the slope of the corresponding point is the reciprocal. Ah, okay, this is actually really good. What do I mean by corresponding? So I mean that, for example, this point right here, -5.02, -2.51, the corresponding point on the other line is when we switch the x and y values. Okay, so the point that was on one function, I want to know what that point would be on the inverse function. All right. So let's take what we have here and take a look at this. So what do you think is the relationship between the slope of corresponding points of inverse functions? And I think we've already said it, use some of those words, but if someone could rephrase that for me, that would be great. All right, so what do we think that relationship is between the slopes of corresponding points of inverse functions? Okay, so the slope slopes of corresponding points of inverse functions. The slopes of corresponding points of inverse functions have or are reciprocals of each other. Okay. So I'm thinking about, like, specifically when we try and explain our reasoning, one of the things I would really like us to start to work on is not using pronouns as much. Okay, so I know this is a math class, but what I mean by pronouns is when we say things like they, or when we're thinking about they, like, what does they mean? And we want to be really specific about that. So the slopes of the corresponding points of inverse functions, that's what we mean by they, right? So the slopes of corresponding points of inverse functions are reciprocals of each other. So we want to be really careful too that we don't just use words like opposite or inverse, right? We want to be specific. When we say reciprocal, that's when we mean the 1/, right? Okay. Let's take a look at another example. Okay. And this one is a little bit different, but also has the same structure, right? So play around with this a little bit and tell me what your ideas are on how we can find slope here, okay? And if we're feeling stuck, like, how do I find the slope in this one? That would be a valid question to ask, okay? I'd love to hear ideas on that because I think this graph is a little bit different from the previous graph. Okay, so if you're a little stuck on how to find the slope, I think Graham put an excellent hint in the chat saying we can find the slope using, I think maybe with the other way around, dy dx, right? Not dx dy, but dy dx and the power rule. Okay, so let's maybe write out what is that equation for the red curve here? That might be helpful. Anybody know what that equation is for the red curve? Yeah, y equals x squared. Now, if we know that these are inverses, what do we think the equation is for the blue curve? Yeah. Okay, so we've got the red curve equation and the blue curve equation. And it might be helpful now if we're trying to find slopes at points to use what we know about derivatives, since we can't necessarily count rise over run on this, okay? So like last time, I would encourage you folks to pick other points, all right? Don't everybody pick one. Pick some other points on here. And let's go ahead and find those points and find the slopes at those points. All right. Does anyone have a point that they are working on? A point on the blue curve? Let's maybe start there. All right, so someone give me a point on the blue curve. 9,3. Okay. So 9,3. Whoop, there we go. Okay, so at 9,3, the slope of the line tangent is, maybe this is where we bring in some math type. We can say, let's see, f prime of x, or f prime of 3. What's the formula for the derivative of the square root of x? That was a mouthful. sorry, 9, not 3. Right, if x, or if f of x, yeah, so if f of x equals x to the power of 1/2, then f prime of x equals 1/2 x, whoops, to the power of negative 1/2. I'm going to ask us to rewrite this without negative exponents and without fractional exponents. Okay, what does that look like? If I were to rewrite this without negative exponents and without fractional exponents. One over 2, so 1 over 2 square root of x. Absolutely. Okay. Now, I did want to take the time to type this because that's something that I've noticed some folks, like, we knew it when that was like sort of the hard thing we had to focus on. But as we've learned all these other rules, sometimes we've forgotten a little bit about that piece. So I just wanted to point that out. Okay. So now let's find f prime of 9. We're going to plug that into the equation we have right there. So we get 1 over 2 times the square root of 9. And what does that give us in terms of a fraction? 1 over what? 1 over 6. Okay. Good, good, good. I think this is a really great point to choose and try. Okay. So at 9, 3, the slope of the line tangent is 1 over 6. Okay. What would the corresponding point be on the red curve? So I would say at what point on the red curve? Okay, so at the point 3, 9, the slope of the line tangent is, now maybe before we fill that out, let's say if f of x equals x squared, then I think this one will be a little easier. What's f prime of x? 2x. There we go. Okay, so if I want to find the slope of the line tangent, I'm going to say f prime of, which will give me 2 times 3, which gives me 6. Okay. Let's try this for one more point. Okay, let's try this for one more point. Someone give me another point. Another point on the red curve. Okay, so at 2.25, comma 1.5, the slope of the line tangent is, and we would say f prime of 2.25. Okay, so we're going to get 1 over 2 times the square root of 2.25 equals, let's see, square root of 2.25 is 1.5, yeah? Okay. So we get 1 over, let's see, 2 times 3 over 2, which reduces to 1/3. Okay. So we see that the slope there at 2.25 is 1/3. So let's see, at 1.5, 2.25, the slope of the line tangent is f prime of 1.5 2 times 1.5 equals 3. Okay. And so that's one thing to be really thoughtful about is calculators are all fine and good, and it gives us things in terms of decimals. But sometimes to see the patterns, we actually need it to be in fraction form. I think it's a little bit easier to see the pattern when we leave things as fractions, okay? So we got 1/6 up here and we got 6 down here. We got 1/3 down here, we got 3 down here. Is this fitting with our pattern, our conjecture, where we said that the corresponding points have slopes that are reciprocals? Is that still a fair statement? Yeah, I think we made a really good conjecture in the beginning. It seems to still be fitting, okay? So on the next slide, I had a chance for us to see if we needed to make any changes, okay? But I think we're good to go. We could say again, the corresponding points or the slopes of corresponding points on inverse functions are reciprocals. All right, so let's do this. Let's pause here. It is 10:36, almost 10:37. Okay, I'm gonna stop sharing this for a moment. Okay, so the last slide that I think is perhaps particularly important in helping you build your understanding of what's going on is this graph right here. Okay, so I believe this is on slide 9. All right, so if you want, you can go back to slide 9 at a later point on your own time and just kind of play around with this, where you can find the red point, find the orange point, and then you see this time they've actually animated it so that the tangent line shows up. And so as you sort of drag these points, then you see what the tangent line might be, okay? And so you can kind of use what you know about rise over run to fill in the slopes, and all the slopes for the orange points, how do you think they will relate to the slopes of the red points? So between the red and the orange, let's say that the slope of this first one is 5. What do you think the slope of the orange one will be? 1/5, okay? And what if I told you that the slope at 2, 12 was -1/2? What would the slope of the orange point be there? -2. Good, very nice, very nice. Okay, so it seems like we've kind of got the pattern here. So I'm going to say, feel free to go back to that activity at your own time. Could be a nice review to freshen up before the exam. But let's go ahead for right now and actually do some examples so we know what it might look like in the context of a problem. Okay, here we go. All right, so for examples 1 through 4, we're going to find the derivative of, let's go back and think about what these mean again in words. The derivative of the inverse function at A, okay? Now, one thing I want to be clear about here, A is the x value of a point on the x value of a point on the inverse function. Okay, so A, anytime you see A, that is the x value of a point on the inverse function. Okay, now the whole reason that we just spent the first part of class exploring this pattern is because sometimes we come across questions where they give us the original function. Okay, so that's what we have here. We have f of x equals this long function. And then they give us a point on the inverse function. So this is an x value on the inverse function. Okay. And so what we want to do is to find the slope of the inverse function at a equals 5, but we don't know the equation of the inverse function. All we have is information about the original function. Okay. So what are some ideas? We've learned about this pattern, but how can we connect that pattern to a question like example 1? And it might be helpful to kind of go back to our inverse function theorem. Okay. How are we feeling? Stuck? Find the inverse and then take the derivative. Okay, cool. So we have this f of x in yellow. How do we find the inverse? How do I find the inverse function? Switch x to y. Okay, so let's start there. X equals 3y cubed plus 4y squared plus 6y plus 5. Okay, so we switched our x's and y's, and now what? Solve for y. Okay. I'm going to go ahead and take one for the team. I'm going to subtract 5 to both sides. Now what? How do we get y by itself? Okay. And now Okay, so I've got this. Did I get y all by itself? Not really, right? We got one of the y's. In particular, we got this y by itself. However, we still have x's and y's in the mix over there. Indeed. Okay. Now, you'll notice that if you sort of look at all the other examples, these are examples where it's pretty gross to solve for y. It's pretty challenging to algebraically find the inverse function. Okay. So I think that's also an interesting idea. So we've learned actually on Monday about how we can handle situations where we have x's and y's mixed together and it's not nice to find or to isolate a letter, right? So let's see. If we switch our x's and y's, well, let's make a note for ourselves that this is a path to, I don't know, this is sort of like the mathematical equivalent of that rainbow wheel of death when you like have something on your computer and that rainbow wheel just keeps spinning and you know everything is freezing but you can't fix it, right? That's sort of like what we're doing here. We're trying something, didn't really work. So I wonder if we can go back to Christina's observation that by switching the x's and y's, we can get an inverse function. And think about this idea of the implicit formula. So this right here is the function of the inverse. Like that is the inverse function. How might we find the derivative of this using what we learned on Monday? Okay, so I get 1 equals 9y squared times y prime plus 8y prime plus 6y prime plus 0. Yeah, I have a situation where the x's and y's are mixed together. It's hard to get the y by itself. So absolutely, we can just think about the y as that random function, right? We could call it g of x, we could call it whatever it is in this particular problem. We just don't know. So we can sort of sidestep that by having the y prime. Okay. Now we did have to solve for y prime. And so I notice here that we have 1 equals, and I can factor a y prime out, 9y squared plus 8y plus 6. And so now I get y prime equals 1 over 9y squared plus 8y plus 6. Okay. So it's actually a really good review of what we learned on Monday. Okay, it does kind of look like a reciprocal. Okay, but let's see if that is intentional or coincidence. So now, in order to find the slope, what do I need to know about? Like in order to find a y prime, that should be 9y squared times, so sorry, my times got a little long, like times y prime. I don't know why I didn't write it for the others. Times y prime, times y prime. Okay, so how do I, like, if I want to get a number for y prime, like I want a number here, what do I need to know in order to get a number? I need to know the y value. Okay, and so let's be really clear here. We need to know the y value of which function? The f function or the inverse function? Well, this that we put a box around in the beginning, this is horrible note-taking strategy, but this function is the equation for the inverse function. Okay, so this is the equation for the inverse. Then we took the derivative of the inverse. So we found our inverse by switching x and y. We took the derivative and we isolated the y prime. So if we're talking about the inverse, then the y value we need right now is actually from the inverse. Does that make sense to folks? Okay. So like, because this whole chain of thought, all of this was all about y prime, or sorry, about the inverse function. Okay, so inverse function, inverse function, inverse function. Now I need a y value of that inverse function. Okay, do I have the y value for the inverse function? No, so sad, so sad. But if we did, that would be totally legitimate, right? Okay, so I really appreciate your patience here. We've sort of tried a few different methods. One where we tried to algebraically grind through it and we got stuck because we couldn't isolate y. Two, we tried to be really clever and use stuff we know, that implicit differentiation, to sidestep it, because that's what we did in a different case. That didn't work out for us because we were, again, so close, except we don't have that one value. So let's try method number 3. Okay, so method number 3. We're going to go back to that formula. Okay, so in words, we know that the slope of the inverse function at 5. Okay, so the slope of the inverse function at 5 is equal to the reciprocal of the slope of f . We're going to leave that blank for right now. Okay. So I'm wondering if you could tell me from, let's say from here, from your original function, if I tell you that a equals 5 is a y value on the inverse, or sorry, an x value on the inverse function, what kind of value is it on the original function? It's the y value, right? I totally blew that. Okay, so what if we wrote this? 5 equals 3x cubed plus 4x squared plus 6x plus 5. Oh my gosh, we had the y value. Okay, we have the y value. This 5 though now is the y value of f. So it's not quite this y value that we need. I know, this is like a lot. Okay. Let's see if we can figure out a value that works for x. Okay. I know this looks really complicated, but I want you to guess and check for a moment. What are some maybe like nice values of x you could try and just see if it works? Like, does it make the equation true? Okay. So take a moment and in your brains or with a calculator, think about some numbers you could plug in for x to make that statement true. 0. Oh, shoot. Okay. So then this means that x equals 0 makes that true. This 0 is what I'm going to put in here. Because if I think about where my x's are, like here, whoops, like here, here, and here, if I happen to plug in a 0, all those terms go away, and then I just get 5 equals 5. Yeah, so then I just get 5 equals 5. Okay. Okay, so now let's go back to this formula. Okay, this is what we want to find. We want to find the slope of the inverse function at 5. So we're going to take the reciprocal of the slope of f of 0. It's the reciprocal of the slope of the corresponding point. Okay. F prime of 0 in this case, or f prime of x, 9x squared plus 8x plus 6. Plug in 0, we get 6. And so our slope of the inverse function at 5 is going to be 1/6. Now, I know that was a very long story, okay? And Ethan, I loved your idea of using implicit differentiation because look what we actually have. This is x equals 0. This is the x value of f, but that also means it's the y value of the inverse function. And what was the number you needed? You needed the y value of that inverse function. So if I plug in a 0 here and a 0 here, what do I get for that y prime in the blue? Y prime. Like the whole expression. Yeah, you get 1/6, right? That's the same answer we got using that third method. We still got 1/6. Okay. I'm glad you find it cool. I'm sure some people are finding this very overwhelming, and that's also okay. Let me put a box around this. Let's walk through another example, but in a more straightforward fashion, okay? So we're going to highlight method 3 to walk through some of the other methods or some of the other examples, okay? Let's go ahead and do example 4. Okay, so let's do example 4. So if we were to use the third method, okay, this is really what I was trying to get at. So if we were to think about this in steps, I would say step 1 is let f of x equal a. okay? Because A is the X value of the inverse, so it is the Y value of the original function. Okay, so let f of x equal A. Solve for x. So in other words, I'm going to say f of x, which is square root of x cubed plus 4x plus 4, equals, in this case, A is 3. Okay. Now, the solving for x part, at least for our cases, involve sort of guessing and checking with nice numbers of x, okay? That is probably the least mathematical thing that we've said in this course, in the sense that we're not necessarily showing it algebraically, but we're using what we know about numbers to kind of make sense of this, okay? So before I do that, because I don't really like to think about square roots, I'm going to square both sides. So I get x cubed plus 4x plus 4 equals 9. And it might even help me to say x cubed plus 4x equals 5 and just subtract that 4 to the other side. Play around with some nice numbers. Whoa, already done. And think about what x could be to make this a true statement. Very nice. X equals 1, right? Because 1 cubed is 1, plus 4 times 1 is 4. So 1 plus 4 gives us 5. Okay. I know, right? Okay, so that's step 1. You're going to let f of x equal A, and you're going to solve for x. The next thing you're going to do is use the formula. So sub into the formula, the derivative of the inverse at A equals 1 over the derivative at the x value that you just solved for. So this x value is this x value. Okay, and this a value is this a value. So let's sub in. We've got the inverse function derivative at 3 equals 1 over f prime of 1. Okay, and so we're going to go ahead and find our derivative. Okay, so our original function was this. I'm going to need to use the power rule and the chain rule. So I've got 1 over 2 times the square root of that times the derivative of that inner function. Okay. And then everywhere I see in 1, I'm going to put, or everywhere I see an x, I'm going to put a 1. So this 1 will go here, here, and here. I'll let you plug those numbers in your own time, but we should end up with 6 over 7. Okay. So I know we took a very roundabout way in example 1, but as a more clean-cut way, here's what we have for example 2, or example 4, okay? Now I do want to point out that Ethan, your strategy of implicit differentiation would also work here. You would still have to do sort of this part, like find the x value, but then you could use implicit differentiation if you did not want to use the reciprocal idea, okay? All right, let's try one more, and I'll do whichever one we don't do together, I will write out on the notes before I post it. 2 times the square root. So the derivative of that square root is 1 over 2 times the square root. So anytime I have f of x equals the square root of x, that derivative is 1 over 2 times the square root of x. Okay. Yeah. Okay. So with these two examples, example 2 and example 3, which one would we like to do together and which one would you like to save for the answer key? Where did okay, so I've got a vote for 3. Great, we'll do this one together. And before we do that, let's answer that question. Where did the x plus 1 come from? Okay, so this is sort of the solve for x in quotations, where we get all the way down to here, x cubed plus 4x plus 5 or equals 5. But instead of solving it algebraically, we're just plugging in nice numbers for x to see what makes it work. Like, what makes x cubed plus 4x equal 5? Exactly. So maybe instead of saying what makes it work, it's like what makes the equation true. Is that a better way of framing that? Okay. So whatever makes this line true, that's where we sort of guess and check with nice numbers. Okay. Thanks for holding me accountable for my pronouns as well. Okay. So let's take a look at 3. Okay, so 3 seems to be the one that we'd like to work on together. And so if we sort of copy our steps over here, we're going to, number 1, let f of x equal a, and then we're going to quote unquote solve for x. And then step 2, we're going to sub into this formula. Okay. So step 1, let f of x equal a, and then solve for x. So I'm going to get 3 plus x squared plus tangent of pi x over 2. And I'm going to say that equals to 3. Okay. And so kind of like I did for number 4, I'm going to start to move some things so I can get x as much by itself as I can. And so in this case, it's just going to be subtracting 3, and I've got x squared plus tangent of pi x over 2 equals 0. And so this is the point where we're going to play the game of what number makes this equation true. Okay. Now, most of these answers will not be complicated answers. They'll be sort of very traditionally nice questions. And so, so that's going to be, you know, something not to worry about. They're not going to be like weird fractions or anything. They're going to be mostly nice-ish numbers. Okay. All right, 0. Let's give that a try and see if that works. I put this in here, I get 0 squared, that part's good. And then this becomes tangent of, what does the inside become? What does pi x over 2 become if I plug in 0 for x? It becomes 0. Okay, so tangent of 0. So this is where, if you took trig with me, I was like, you need to know your unit circle values. You need to know your unit circle values. And this is precisely the context where it becomes useful, because we need to remember what tangent of 0 is. And it turns out that tangent of 0 is 0, which is why we can say x equals 0 satisfies this equation. Okay. All right, we've got our x value. We can highlight it in that neon green, and then we can move on to step 2, where we're going to sub into our formula the inverse function derivative at a equals 1 over the derivative of the original at x. And so we'll have our x value down here. We'll have our a value in here. All right. So we'll get this equals 1 over, let's see, now we have to take the derivative of that piece. So derivative of 3 goes to 0. Derivative of x squared is 2x plus, someone help me out here, what is the derivative of tangent of pi x over 2? I believe it's going to be a secant squared, but I would argue that the inside is not x. Pi x over 2, okay? And because it's not just an x, what rule do we need to keep in mind here? We need to use our chain rule, okay? So what are we going to multiply this by? In other words, what is our derivative of the inside function? Pi over 2, exactly. So we're going to multiply by pi over 2. That takes care of our chain rule. And now we just need to plug in everywhere we see an x, we're going to plug in 0. So this will be a 0 and this will be a 0. And so we'll get 1 over, let's see, the first term goes away. We have secant squared of 0 times pi over 2. Ooh, secants. I don't remember my secant values, but I hope we remember our cosine values. Maybe we could think about it like 1 over cosine squared 0 times pi over 2. Anybody remember what cosine of 0 is? Cosine of 0, 1. Okay, so this becomes 1 over 1. So I end up with 1 over pi over 2. And what does that become if I simplify that even more? 2 over pi, very nice. Okay, so our slope there is going to be 2 over pi, all right? So just to kind of review before we move on, that example number 1, we did an excellent job, maybe the most outstanding conversation that I've actually had with a class around how do we find this derivative, okay? So genuinely thinking about what we know, which is I know that inverses mean you switch the x and y, so let me try that. We got a little bit stuck, which is fine. But then to have a backup plan that was like, how does this tie into something we learned before and use implicit differentiation? Such an awesome idea, okay? It turns out that through a lot of this trial and error, folks have come up with sort of this 2-step process in which we could use the formula we learned on the other page, the pattern we noticed from Desmos to kind of use that to find the slope, okay? All right, so derivatives of inverse functions, not necessarily something we see a ton on. Okay, so let me answer that question just a second. But it sort of leads into where these formulas for inverse trig functions come into play. And for those of you who are planning on taking Calc 2, these come up a lot in Calc 2 or Math 151, okay? We're not going to use these a lot in this class. We will a little bit for some practice, but you're going to use this a lot in Calc 2. Okay, this is one of those things, it's like kind of squirrel this away for Calc 2, but learn how to use the rules in Calc 1, okay? Now, to kind of address Marissa's question about how would you know to use this strategy on a test, the questions tend to look very much like this. Like I'll say, here is an original function. And here is a value on the inverse function, but I'm not going to tell you what the inverse function is. Okay, and when you see that kind of setup, you should be thinking, let me solve for x, and then let me use that reciprocal formula to find that slope. Does that make sense? Okay. Great question, by the way. And I think those are exactly the kinds of questions we should be asking ourselves. Like, how am I going to know when this comes up on a test, right? Or how am I going to know in some random problem in like 2 months, which one to use? All right. So here we go. We got this one last part of chapter 3. Hang in there. You guys are doing so well. Derivatives of inverse trig functions. So all of these, we can use the formulas that we just learned to derive them. I will not do that to you right now, but you can certainly look that up in your own time. Instead, let me tell you the formulas. We are going to do this in a specific order. I know sometimes when we see tables, people like to start here and go here, and then here, and then here, okay? The way I'm going to fill out this table, I'm actually going to start here. I'm going to go all the way down, and then I'm going to go across, and then I'm going to go up. All right. The reason why is because these formulas are kind of gross looking, but there are patterns within the grossness. And so when I write it this way, and then this way, and then this way, it helps me remember those patterns a little bit better. All right. So the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. Okay, I'll give you a moment to write that down. Exactly. Order in chaos. And yeah, these aren't the nicest formulas, but okay. Now, if I know inverse sine, turns out I also know inverse cosine. It's going to be the same thing. However, remember that trick I said where all the derivatives of the trig functions that start with a c, those are all negative? Same rules here. The only difference between the inverse sine and the inverse cosine derivative, one is a positive, one is a negative. Okay, so that's why I like to start with these two, because if I know one, I know the other one. All right, the tangent, the inverse tangent one, 1 over 1 plus x squared. What do we think the inverse cotangent one is? Negative 1 over 1 plus x squared. Exactly. Okay. So my method to my madness, these two pair, then these two pair it together. Same thing, but opposite signs. And then I'm going to do these two last. All right, the derivative of inverse secant is 1 over the absolute value of x times the square root of x squared minus 1. Make sure you get that absolute value, make sure you get that x squared and then the minus 1 afterwards. Okay. But if you know this, you know inverse cosecant. Same thing, opposite sign. Negative 1 over absolute value of x square root x squared minus 1. Okay, so that's why I like to start here, head down to tangent, go across for cotangent, and then head back up for cosecant. It is not the most attractive. No, it is not. Okay. All right. If we were live in class, I'd be like, raise your hands if you think you're going to be taking Calc 2. You don't have to do that right here, but if you are planning on taking Calc 2, let me just highlight. Yeah, there we go. You could raise your hands that way. Cool. All right. So if you're planning on going on to Calc 2, little spoiler alert, not really a spoiler, but this one comes up a lot. This one comes up a lot. The other 4, not so much. Okay, so inverse sine and inverse tangent come up a lot. The other ones less frequently. Okay, but you'll be using those not with derivatives, but with antiderivatives. Okay, so keep that in mind. But for us, let's focus on these last 3 examples. Oh, yeah. So we're learning like all about derivatives, and we're going to do a little bit about going the other direction, like antiderivatives. Okay. So it's almost like, imagine we're learning how to add and all we're doing is addition, but then at some point it's really helpful to know how to do subtraction. It's basically like that. Okay. Exactly. All right, so for examples 5 through 7, find the derivative. So it's more about recognizing the rules and then applying these new equations, okay? So when I look at example 5, the first rule I might see is the inverse trig, but I sure hope I see another rule in there. What is that other rule? Chain rule, yeah. Okay, and the giveaway for our chain rule is we sort of have this outside piece and we have this inside piece, okay? And so if I want to take my derivative, I'm going to take the derivative of the inverse cosine part, and I'm going to multiply it by the derivative of the inside part. And let's see. I know that the green part is going to be 2x, right? What do we think the derivative of the pink part is going to be? Ah, yes. So good, so good. Okay, so negative 1 over that part, totally fine. Square root of 1 minus. Yes. Okay. Now this is why I'm making a big deal of it, right? Because it's x squared. But like anytime we use chain rule, that inside piece actually doesn't change the first time. So it's not just x squared, but it's x squared squared. All right, and that's just because this x means that that's squared. And if we're going to have x squared, we need to put the x squared inside of the square. Okay, so really great observation, Eric. All right. Good news is not a ton to simplify. We can say negative 2x over the square root of 1, oops, minus x to the 4. Done. Okay. Nice, nice work. Yes, what's up? Does someone have a question? No? Okay. All right, let's try example 6. All right, so yes, there are more rules now, but before we even get into that, let's list out the rules that might be useful to help us solve example number 6. What do we think is going to be helpful? Inverse trig. Power rule, good, and product rule, so good. All right, so let's set up our product rule. U equals x squared. I think we all know well by now that du will equal 2x. All right, and v equals inverse sine of x. And so what does that give us as our dv? Good, 1 over the square root of 1 minus x squared. Now, is it okay right now that I have the x squared here, or does that need to be something else? Because last time, like in example 5, it was x squared. So are we okay here? Yeah, we are, because this is just x. Okay, so whatever is in that green bubble needs to be in the green bubble below. Okay. All right, let's string this together and get our derivative. U dv plus v du. And we've got x squared times 1 over root 1 minus x squared plus v times du. Okay, and not a ton to simplify here. Maybe just taking this first term and stacking it like a single fraction. X squared over root 1 minus x squared plus 2x inverse sine of x. Okay. Again, really, truly don't worry about the simplification, okay? I think it's more important that you show me you know the rules, you know how to apply them, and you can get to some sort of solution, okay? Real quick though, what is another way to write inverse sine? Maybe we'll go back up here. And there's another way to write inverse sine. It is actually not 1 over sine x. Okay, that is one of the weird things about that notation. It is though the arc sine. Okay, so I just want to point that out because I think that for folks who took trig with me, we kind of use both interchangeably, but some professors prefer the one with the -1 and some professors prefer the arc sign. I just want you to know that they're the same. So if I wanted to say inverse cosecant, I could actually say arc cosecant x. That would be the same thing. Or instead of inverse tangent, I could say arc tangent, and that would be the same thing. Okay, so if you've been sitting here being like, I don't know what this means, it's the same thing as the arc sine or the arc cosine or the arc tangent. Okay. All right. One last question here. We want to make sure we know how to apply things in a different context, right? So if the position of a particle at time t is given by s of t equals the inverse tangent of 1 over t, find the velocity of the particle at time t equals 1. So lots of different concepts together here. What do we need to do? What are we given? What do we need to find? We need to find that velocity. Okay. Well, how do we find a function for velocity in general? Perfect. We want to find the derivative of the position function. Okay. That's going to require us to take this derivative. And maybe, since I'm taking a derivative, maybe I'm going to write it like the inverse tangent of t to the -1 power. Okay. Whoa, no. Okay. All right, so derivative, what rules are we going to need to use to find this derivative over here? Chain rule, excellent. Chain, we can say inverse trig 2. Okay. And so when we take our derivative, we've got derivative of our sort of outside function and our derivative of the inside function. All right, so derivative of inverse tangent is 1 over 1 plus something squared. What goes inside that something? One over t, exactly, because this should be the same thing as this. Okay. Times the derivative of the inner function, we get negative t to the -1 minus 1. Okay. Now I do have to say, I'm seeing some folks make mistakes when they take derivatives with negative powers. These same folks who are making mistakes are not writing this out. Okay. I'm not saying that if you write it out, you will 100% get it right, but I bet you'll make fewer mistakes if you write it out. Okay. So that's why I try and model that here, because I want to have you avoid making those mistakes. Okay. So let's clean this up a little bit. 1 over 1 plus 1 over t squared times -1 over t squared. And I'm just trying to find the value. So I'm going to leave it like this. And now I'm just going to plug in 1. Okay. If I'm trying to plug in a number, I'm not going to try and simplify too much. I just want to write it with powers that I can see preferably positive powers, so it's easier to do the mental math in my head, okay? So I've got 1 over 1 plus 1 over 1 squared times negative 1 over 1 squared. And when we do that, what do we get? Let's see, 1 over 1 plus 1 times negative 1 over 1. I think we get negative 1/2. Okay. So let me sort of zoom back in. These are the last 3 examples we worked on today. How are we feeling? No idea, like you're not sure, or like so bad that you're like, I have no idea. Okay. 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 Well, here's what I want to have you sort of think about if as you're sort of studying for exam 1, or exam 2 rather. It would be important to know these formulas. Okay, so these derivatives of inverse trig formulas, like alongside all the other formulas we have for derivatives, we do want to sort of add these to the list. Okay. We use them a lot in conjunction with other rules, right? So as we sort of study for Friday, we really want to be thoughtful about having, like, being able to identify the rules that we need to go into it. We really want to make sure that setup is pretty good, okay? Now, if you were feeling sort of overwhelmed by specifically our work in example number 1 over here, I would encourage you to, like, if you're like, I just don't understand the conversation, I would ask you to focus more on sort of this 2-step process that we did for example 3 and example 4. Okay, so when we're thinking about our setup here, it really boils down to let f of x equal a and solve for x. That's 1 step. And then step 2, sub it into that formula. Okay, so if you're like, I don't really know how to, like, approach the inverse kinds of problems, to boil it down to step 1, step 2. Okay. Again, I think the benefit to our conversation earlier was more around practicing how to be mathematicians, because the actual content, I could have given you this formula in 2 steps and we would have been done in like 30 minutes. Okay. But I think there's value to seeing where all these things come from and why they are. But as far as the exam, in terms of procedure, you can study that procedure. Okay. So I hope that helps maybe center us a little bit more in terms of like where to focus our time and energy. I know that we all have, a lot of other classes that we're taking or other responsibilities in life, including self-care. That's not less important. But I think that sometimes it can be easy to get lost in the, conversation. And the bigger takeaway here, I think, in terms of Friday is just sort of like those 2 steps. Okay. So I hope that helps a little bit. Let's go ahead